Now, in the previous class, I was talking about this particular problem, that the question I am writing it in a formal way. Once again, that prove that the set of n cross n matrices, having trace equal to zero is a subspace of M n cross n f. And I'm going to use example 18, the statement of example 18, which I'm considering as a theorem actually to prove this particular result. If someone wants to prove this result using the definition, the statements given in the definition, he can do so. If someone wants to prove this result using the statement of theorem 1. What was the theorem number? Theorem 1.3, he can do so. I'm considering example 18 as a theorem, and I'm going to use it over here to show that, yeah, it is true, because example 18 is the strongest example, the strongest theorem. So how to write this particular solution? Let us discuss it. We know that M n cross n f is a vector space. If you ask me from where I have selected this particular problem, you go to page number 18 and see example 4. Page number 18 of the book and example 4 that I'm actually trying to solve for you. So we know that M n cross n f is a vector space, and it is a set of all square matrices the matrix element has been chosen from field capital F, and M n cross n f is vector space with respect to matrix addition and scalar multiplication. You need not write all these in the examination if the examination is offline. I'm talking about the offline examination. Probably you will be sitting for online examination, so don't have to worry. This is a kind of, this paragraph which I have written over here is a kind of recapitulation of the thing. But it is also true that not every square matrix has trace equal to 0. I can consider this square matrix 1 0 0 1. This square matrix is the identity matrix where trace of I is equal to 2. It is not equal to 0. So here the subset of this vector space, the subset that has been considered over here is the following. Let us denote this by, say for example, M prime n cross n f. This is the subset of the set M n cross n f, where each element present in S has trace 0. Only those square matrices have been considered over here, whose trace is 0, whose trace are 0. That is the set capital S, and we need to show whether this particular set is a subspace or not. If I stick to the statement of example 18 of the exercise, then first of all, we need to show that the zero vector also, zero vector of the vector space also belongs to the subspace, the subset. We know, number one, that zero vector of the vector space m n cross n f, the zero vector of the vector space m n cross n f is the zero matrix of order n cross n, which looks like this. This is the zero matrix. Okay, and if I denote this zero matrix by 0 bar, then obviously the trace of 0 bar will be the sum of the diagonal elements, which is equal to 0. Since the zero matrix is satisfying the property here is the following: the trace is 0. This is the property that needs to be satisfied. So since it is satisfying this particular property, therefore this implies this zero matrix 0 bar belongs to m prime n cross n f. We selected the zero matrix from the vector space m n cross n f. Here we actually selected this from m n cross n f, and as soon as we found that it is satisfying this property, that means it also belongs to the subset. Okay, so the first property is satisfied. Next we need to show the property 2. So in property 2, we need to, if you look at the statement of the example 18, we consider an element A belongs to the field on which the vector space is defined, and we also consider two square matrices, capital A and capital B, from m n cross n, m prime n cross n f. Remember, just look at this from where I am selecting. I'm again writing the statement which is there in the example 18. In example 18, it was said that ax plus y belongs to W whenever A belongs to F and x comma y belongs to W. Now my F I have chosen here. This F is a field. It can be the set of real numbers. It can be the set of complex numbers, anything. This X and Y, this X, in my case, this X is actually the capital A and the Y is capital B. And my W is this particular set where the trace is 0. Now capital A and capital B are matrices, and they are square matrices, and they belong to this particular set, and therefore their trace is 0. So this implies that capital A and capital B are square matrices, and trace of capital A is equal to 0 and trace of capital B is equal to 0 because I've selected them from here. Now we shall consider this element. We shall try to form this element. I mean, not this one. We shall try to form this element. Now, A x plus y. My x is capital A. My y is capital B. Acha. Since capital A and capital B are square matrices, so we can consider the form of, we can consider these matrices as follows. We can write these matrices in the following manner. Okay. A n1, A n2, nn. This is the form of capital A, and capital B is of the form B11, B1n, Bn1, Bnn. And by trace of A, we actually mean A11, A22 plus Ann. By trace of B, we actually mean B11 plus B22 plus Bnn. Now, if I calculate this expression, what will I get? We will substitute the form of A and the form of B over here, like this. And you know how we multiply this. What do we mean by scalar multiplication? When we multiply a vector by matrix by the scalar, actually every element, individual element gets multiplied by it. So I'm writing it in this way. And this I'm writing as it is. Okay. And then you can add them up. So we'll get AA11 plus B11. In this manner, AA11 plus B1n. In this way, AAN1 plus BN1 and AANN plus BNN. Okay. This is the form of the matrix which has been constructed here. And you see that if I try to, I can name this matrix as capital C. And you see that this trace of, if I take now the trace of C, what will I get? We will get AA11 plus B11 plus AA22 plus B22 plus plus AANN plus BNN. Now, if I rearrange the terms, we will get AA11 plus AA22 plus AANN plus B11 plus B22 plus plus BNN. Okay. And you know from this that A11 plus A22 plus AAN, this is 0. B11 plus B22 plus BNN, this is 0. So this term is 0. Second term is 0. So trace of C is equal to 0. And which implies that A plus B belongs to M prime n cross n F. So you see, you carefully observe all the conditions. If I go from the beginning, all the conditions of this statement of example 18, are actually being satisfied over here. Why to use the definition? Definition is only for understanding. Never use definition to solve a particular subset to whether it is a subspace or not. Always try to use the strongest version of the theorem. So I will recommend example 18, which is the statement of the theorem you must use to show that a particular subset is a subspace of a vector space. So we first started with the vector space, then we design the subset, and obviously capital S, I must write it over here. Capital is obviously non-empty. It's a non-empty subset. Obviously it is non-empty, and therefore and then we actually try to show that whether the zero vector, which is the zero matrix, is an element of the subset or not. So we successfully showed it over here, and then we try to show that this particular property is also getting satisfied. You see in the book, the example 4 is only written. Its solution has not been shown. So there are many examples like this where the solutions are not given, but the way by which you need to proceed is that I actually showed you over here. For every other problem, you need to follow in the same manner. But if you do not know the vector spaces and what sort of vector addition and scalar multiplication are used, then you will not be able to solve the problems. Okay, so you have to deal with some set of matrices. You have to deal with the set of n tuples and the set of polynomials. These will be the important vector spaces that needs to be discussed. And in example 5, suppose if I consider example 5 of the question of page number 19, if you have the book, it is written that the set of matrices, in M cross N R having non-negative entries is not a subspace of R, not a subspace of M cross N R. Now you see, what does this mean? This is an example of a subset which is not a subspace. What is M cross N R? M cross N R is the set of all matrices whose order is M cross N. It is not talking about the square matrices. It is talking about the matrices of any order. What is R? R is the field. So the matrix elements are all real numbers. Now it is saying that if we consider the set of all matrices of any order whose elements are real numbers, and from there if I select a set which consists of only those matrices where the matrix elements are all non-negative entries, then this particular subset of containing the matrices with non-negative entries will not be a subspace. Why is it so? Because one of the properties will be violated over here. For example, if I consider, say for example, any general matrix I'm considering, say A11, A12, ... A1n, A21, A22, ... A2n, AM1, AM2, ... AMN. These are, suppose these are this is a matrix belonging to M cross N R, because the order of the matrix is M by N, and all these Aij's are suppose real numbers. Okay. If I consider now that all these Aij's are non-negative, then this particular set, this particular matrix will satisfy the condition given in the problem. So if such and such matrices are considered only, where the matrix elements are all non-negative, this will not be that particular set will not be the that particular set will not be subspace, because in the definition it is written that W must be closed with respect to scalar multiplication. W must be closed with respect to scalar multiplication. So if it means, according to this particular statement of the definition, it means that if I multiply this matrix by any scalar A, then the outcome is also a matrix, but its entries has to be non-negative also. Then only it will belong to that particular set. For example, if I take 1, 1, 1, 1, if I multiply this by 2, we get 2, 2, 2, 2. So 1, 1, 1, 1, this matrix is a square matrix and it has all non-negative entries. When we multiply this by scalar, it is again non-negative. But what happens if my A is less than 0? If I take this scalar quantity to be negative, and if I multiply this scalar by the if I multiply this matrix by the scalar, then the elements will become negative. So if A is 0, A is negative, suppose A is -1, then the outcome of this multiplication will become minus A11, minus A12, minus A1n, minus AM1, minus AM2, minus AMN. It is no longer a non-negative element. It will not belong to the set, and therefore W, the so-called subset, is not closed with respect to scalar multiplication. So therefore it is written in example 5 that this particular set is not a subspace of the vector space M cross N R. Now I will ask the students to unmute themselves and tell me whether they have understood what I have discussed so far, or if there are any doubt. If there is any doubt regarding the understanding of this particular thing, you tell me. In this exercise, you have to follow the same rules to show that a particular subset is a subspace. You need to show the same, you need to follow the same rule. So any doubt?
Sir, while proving this, do we have to write all this point which you said?
Yeah. If you are sitting for offline examination, then your answer must start from here, because the examiner knows what we mean by M cross N F. The examiner knows this. It is just a recap thing that I have written. Okay. So you can start from this particular point. And then you have to write the entire calculation that I have shown in the next page. Starting from here, you have to show everything until you reach to this particular
point. We are going to get the recording of this class.
Yeah, sure. The recording, the class is being recorded. You are going to get the recording. But that is a separate question. You have asked me the first question that you have asked me, that whether you need to write everything or not. Answer is yes.
Yes, sir.
Now, since you will be sitting for the online examination, so in online
examination, you're talking about semester exam.
Semester exam. Probably you will be the high chance that you will be sitting for online examination. So in online examination, you will be probably this sort of question will be asked with as a MCQ type. So you have to just very short questions, whether this is a subspace or not. If it is not a subspace, why it is not a subspace? You are going to sit for you have already given the type of prerequisite examination where KD sir set the question paper. So you have seen what sort of MCQ type of questions can be set. And then I'll be taking the examination of CO2 in on Sunday probably. So there also you'll find that what sort of questions can be asked from there. So this is a question. The question can be set in the following way. So for example, I'm asking the set of matrices having non-negative entries is not a subspace. Option number 1, because 0 element doesn't belong to it. Option number 2, all the elements are not having the non-negative entries in the subset. Option number 3, it is not closed with respect to vector addition. Option number 4, it is not closed with respect to scalar multiplication. Which one is the option? This sort of question will be asked in MCQ type of problems. Any other question? Any other doubt? Bolo.
Sir, in the previous question, instead of writing all the elements, can't we just use the property of trace to prove it?
I mean, you are asking me whether you have to show the explicit form of A and B or not.
Yes, sir. I can just take the trace of A into A plus B and then use the property that we can take the constant out, A into trace of A plus trace of B, and then I can show that it is 0.
Yeah, you can do so. You can do so, but what happens is that in matrix theory, in many colleges, the trace portion is not.
I was talking about this thing.
Yeah, in many colleges, the trace portion is not there. The trace part is not there in the syllabus. So probably many students do not know the properties of the traces. Probably because there are so many students and they come from different boards. So what you are saying is the following thing. It makes the thing, it makes the thing very simpler. Obviously, but I'm not sure whether every student is well aware of these properties of traces or not. So if they are well aware of the properties, then they can use it, no problem. You are going to get full marks for this. If not, then you have to show it explicitly. It depends upon whether you know it or not. Any other question? Now, I have a point to make. The point is that, see, if you have the book with you right now, in page number 20, so many exercises are there. So many problem exercises are there. So I will not ask you to solve each and every exercise because it is not possible. The time is too short. Try to select those problems which you are comfortable with. I'm leaving this up to you. If you are not, probably, I'm considering the example 31, exercise of the exercise. If you are not comfortable, I think it would be, I mean, if I share the screen of the book, then probably it will be good for you. Let me share the screen. Probably you are able to see my screen. And then I'm here. And then this. Yeah, I'm talking about this portion. Now I'm talking about this page exercise. You see, there are so many problems out there. Let me mark a few important problems for you. That will be, I mean, you'll find it comfortable. Say, for example, if you ask me, sir, please mark a few problems for us so that we can try it at home. So I will say that you try problem number 8. Then you can go to, okay, mark is still there, sorry. Problem number 8, then you can, I'm marking, say, for example, just a minute, where is it? Okay, then you can try 10, 11. We can try, if you have, yeah, you can try 12. if you have if you have done all the vector spaces, if you have identified all the vector spaces that are there in section 1.2, various types of vector spaces are given. So if you have studied that, then you can do question number 13. Otherwise, if you are not if you do not know what do we mean by FSF, then you will not be able to show it. If someone, so those who can identify FSF to be a vector space, they can prove this part, they can solve this particular problem 13. Those who do not doesn't who are not able to identify it as a vector space, they will not be able to. If you do not know what CR is, you will not be able to do it. If you know what CR is, you will be able to do it. So whether you know the vector space or not, that is very important. Another important problem that you can try is the following. This is the problem. It's a very important problem. I mean, I will mark it star. Try to solve this problem. Try to think of. It is saying that, for example, okay, regarding this particular problem, I must tell you something. If you go back to this page number 19, you will see that in theorem 1.4, it is written that any intersection of subspaces of a vector space V is a subspace of V. Any intersection of subspaces of a vector space V is a subspace of V. What do you mean by this particular statement? It means that a capital V is a vector space and S1 is a subset of V, subspace of V, S2 is a subspace of V, S3 is a subspace of V. Then if you take the intersection of this, that will be subspace of V. If you take intersection of that, it will be subspace of V. If you take intersection of this will be a subspace of V. If I take an intersection of this, it will be a subspace of V. So any intersection of subspaces of a vector space is a subspace of V. It has been proved very briefly, and this proof is it's complete proof. It's nothing is missing over here. So everything they have written. So this always holds, but it is not true for the union. So if we have a vector space and if you have S1 and S2, then if S1 is a subspace of V and S2 is a subspace of V, then it doesn't always imply that S1 union S2 is a subspace of V. So first of all, you need to prove this, that you need to find out a particular problem, particular vector space, and you have to consider a subset, two subsets, which are subspaces. But when we take their union, this is not a subspace. First of all, you have to find out a counter example, and because S1 union S2 is not always a subspace, and then you come back to this particular problem. You come to this particular problem. In this particular problem, what is written is a condition given over here. What is this condition? Condition is, sorry, just a minute. The condition is, if V is a vector space and if V is a vector space and W1 and W2 are two subspaces of the vector space, then W1 union W2 will become a subspace of the vector space if one is contained in the other. If W1 is a subset of W2 or W2 is a subset of W1, not both, then W1 union W2 will become a subspace of the vector space. Otherwise, it is not always true. So first of all, you have to find out a counter example where it is not holding. Then you can try question number 19. Okay, so this question number 19 is actually very important. If you can't solve it, I will help you in this regard. Now you see in this particular definition, in this particular exercise, two definitions are given. First definition is about that this definition is saying about the sum of two sets. What do you mean by sum of two sets? We always know that two sets are combined according to their with respect to the operation union, but here something different has been considered. Two sets can be added also. This is the definition, and this particular definition gives you the definition of direct sum. So try to identify this definition. Try to read these definitions first of all. Try to identify what it is saying, and then you can try the subsequent problems. You can try question number 23, 24. Then you can try question number then you can try, just a minute, where is it? 23, 24, and then you can try 26 and 27. Then you can try 28, 29. Up to 29, if you try, if you solve this much, I think you will be in a position to understand what is happening and what sort of thing that we need to show and how to proceed with the problem. So if you do up this 9 or 10 problems, not these 31 problems I'm talking about, if you do a 9 or 10 problems from this particular exercise, you're definitely going to understand what is happening over here. So any other question?
Sir, can you please show an example where that S1 union S2 is not, I mean, not a subspace of the original vector space?
You want me to do it, but you will not think.
No, sir, I gave it a thought, but I can't think of anything. Okay, sir, I'll give it another.
Okay, no, what is your name?
Sir, Anubhav.
Anubhav. Now I'll first of all, think about this upcoming CA2 exam. Prepare yourself for this. After CA2 exam on Monday, you can WhatsApp me or you can call me. Okay, and you can ask me if you have thought of any problem. You can ask me that, sir, is it all right? I will say that okay, no. Either I'll say that yes, it is all right, or I'll say that no, it is not all right. Then only first of all, you give a thought that what sort of vector space is there where S1 is a subspace, S2 is a subspace, but S1 union S2 is not a subspace. If I give you this particular answer, then I mean, you will not feel it. I mean, this linear algebra is a kind of subject where you have to think by yourself. You have to read, you have to study. If I give you every answer, then you will not work it out by yourself. So I'm not saying it right now, but in the
sir,
after examination, once you give it a try, then if you can't, then you call me. I'll say to you. Okay, and after this session is going to end. Now some of the students are asking about this echelon matrix, echelon form. So in the next session, please join in the next session. Next session will not be recorded. So in the next session, I'm going to discuss about it. I'm going to deal with their problems. Okay, and we missed one class because of the registration process. So in this week or after the CA2 examination, I may set one date extra date in which we shall again meet, and I will take a class, because otherwise it will not be possible for me to complete the syllabus. The missing class has to be rectified.